if you were to add enormous amounts of mass, the geometry would curve dramatically. The rules for how objects move stay the same, but the results look different because the stage isn't stable. This flexibility of geometry becomes even more interesting when you consider that geometry can store information. If two massive bodies orbit each other for millions of years, they shape the surrounding curvature in a way that reflects their motion. When they merge, the resulting gravitational waves carry that information outward. The waves don't just show that something happened, they reveal exactly how it happened. The shape of the waves contains data about the masses, their speeds, their spins, and the final object they form. That's not something you expect from geometry if you're thinking of it as a static idea. That's something you expect from a physical medium or a field. It suggests that geometry behaves more like a participant than a background. Another way geometry shows its dynamic nature is through the influence of energy. Energy doesn't have to be in the form of mass to curve space-time. Light curves space-time too. Radiation curves space-time. Pressure curves space-time. This means geometry listens to more than just matter. It listens to anything that carries energy. In the early universe, radiation was abundant, and its presence played a role in shaping the geometry. This is part of why the universe evolved the way it did. The geometry wasn't responding only to matter, it was responding to energy everywhere. Then there's the question of whether geometry is fundamental or emergent. Some theories propose that space-time is made of something deeper, something we haven't identified yet. If that's true, then its dynamic nature could be a sign that geometry is a large-scale effect that arises from smaller interactions. In that case, the living quality of geometry might be a reflection of an underlying system behaving collectively. It would be similar to how temperature arises from the motion of particles. No single particle has temperature, but a group of them does. Geometry might work the same way. No single microscopic component would have curvature, but a large system of them could create curvature collectively. If geometry is emergent, then its responsiveness might make perfect sense. It wouldn't be a rigid structure. It would be the result of countless interactions working together, always adjusting to new conditions. This idea is still speculative, but it does show how far the concept of geometry has drifted from the simple shapes of early mathematics. It has become something richer, something that behaves like a system in motion, something that records the state of the universe while continually adjusting to it. There's a particular kind of quiet that surrounds the objects sitting at the far extremes of what we understand. That quiet isn't the kind you get from lack of information. It's the quiet you feel when you're standing near something that contains more answers than you know how to ask for. Black holes in the edges of the observable universe fall into that category. They're not just strange, they're places where the familiar rules begin to stretch, bend, and eventually stop cooperating. And in that misbehavior, they reveal clues about space-time that don't appear anywhere else. They show us the parts of the universe where our theories reach their limits, where the math we trust starts whispering that something is missing. Black holes are especially good at exposing those limits because they make gravity so intense that space-time curves in ways that challenge every assumption we usually rely on. If you picture a star much larger than the sun collapsing under its own weight, the gravity eventually becomes strong enough that nothing can escape it, not even light. From the outside, you can still describe the gravitational field, the rotation, the temperature of the surrounding material, and the radiation emitted as matter spirals inward. Those pieces follow the equations of relativity with remarkable precision. Yet the closer you get to the center, the more the equations push towards something they weren't built to handle. At the very core of a black hole, according to relativity, the curvature of space-time becomes infinite. It's not just a steep drop. It is a point where the equations stop providing meaningful answers. That point is called a singularity, and it represents more than a location. It's the place where the mathematics breaks down so completely that it becomes clear something deeper is missing from our understanding. Singularities aren't physical in the usual sense. They're warning signs. They tell us that the model we're using has reached its limit. Relativity can describe the outside of a black hole beautifully. It just can't describe the inside in a complete way. Quantum mechanics doesn't help much at first glance. If you treat the inside of a black hole using quantum rules, you end up with contradictions that are just as severe. Quantum theory doesn't allow infinite densities. It doesn't allow space-time to collapse into a point. But relativity insists that's exactly what happens. The two theories disagree so strongly that they can't both be right in that environment. And since black holes are part of the universe, they force the question of what replaces the singularity once the missing theory comes into view. Another clue hiding in black holes appears when you think about what happens to information. If something falls into a black hole, its details seem to vanish from the universe once it crosses the event horizon. The event horizon is the boundary beyond which nothing can return. From the outside, you have no way to know what fell in. You can't see whether it was a rock, a gas cloud, or an entire star. All of the specific information seems lost, but in quantum mechanics, information must be preserved. It can transform, spread, or become nearly impossible to recover, but it cannot be destroyed. This principle is built into the framework of quantum theory. So when you place quantum mechanics next to black holes, another contradiction forms. The black hole seems to erase information. Quantum mechanics says that cannot happen. This disagreement led to the famous information paradox. It's one of the clearest examples of how black holes reveal gaps in our understanding of spacetime. Einstein's theory predicts that information disappears. Quantum mechanics predicts that it doesn't. Both systems have been tested thoroughly. Both describe enormous swathes of the universe with incredible accuracy. Yet they cannot agree about something as fundamental as whether the universe loses information. This paradox has pushed scientists to explore new ideas, including the possibility that the information might not truly vanish, but instead be encoded in the surface of the event horizon, or released back into the universe in a subtle way through radiation. That radiation, often called Hawking radiation, adds another layer of complexity. According to quantum mechanics, black holes aren't perfectly black. Virtual particles appearing near the event horizon can lead to the black hole slowly losing mass. Over incredibly long periods, the black hole evaporates. This evaporation process suggests that black holes have a temperature, which is something relativity alone does not predict. It also means that black holes can disappear over time, but if they evaporate entirely, what happens to the information trapped inside? Does it evaporate too? Does it leak out? Does it become encoded in the radiation? No one has solved the puzzle completely, but the existence of the puzzle itself reveals that black holes carry hints about the nature of space-time that we haven't yet deciphered. Black holes also challenge our understanding of space and time in a simpler but equally puzzling way. As you fall into a black hole, the geometry shifts around you so drastically that time and space behave in unfamiliar ways. From the viewpoint of an outside observer, you appear to slow down as you approach the event horizon. They never see you cross it. They see your motion freeze, your light becoming dimmer and stretched. But from your viewpoint, time moves normally. You cross the horizon without noticing anything unusual. This disagreement isn't an illusion. It's a natural consequence of the geometry. It shows how deeply tied our experience of time is to the curvature around us. And black holes amplify this reality to an extreme degree. Their edges reveal something subtle about space-time too. The event horizon isn't just a surface. It's a boundary where the idea of distance becomes deeply dependent on perspective. For someone falling in, the horizon isn't a special location. But for someone watching from far away, the horizon marks the limit of visibility. It's a surface defined not by physical material but by the structure of space-time itself. That makes it a geometric boundary, a place where the usual relationships between inside and outside break down. Understanding that boundary requires understanding how space-time organizes itself under extreme curvature. Another place where clues hide is at the very edge of the observable universe. When you look outward, the light you see from distant galaxies has been traveling for billions of years. The universe has expanded while that light traveled toward you, stretching the wavelengths and creating the redshift that astronomers measure. But the light only reveals part of the story. Beyond a certain distance, galaxies are moving away faster than light due to the expansion of space. That means their light will never reach us. The edge of the observable universe isn't a physical edge. It's a limit created by the speed of light and the expansion of space-time. And the fact that this limit exists tells us that space-time behaves in ways that relate directly to energy, pressure, and the curvature of the universe. The expansion also raises the question of what lies beyond what we can observe. If space-time stretches faster than light can cross it, then there are regions we will never see. They exist, but they are forever beyond our observational reach. Those regions are cosmic edges too, not because space ends, but because our ability to see them does. These edges reveal how limited our viewpoint is and how much of the universe remains inaccessible. They also force us to consider whether the geometry of space-time changes in regions we cannot observe, and whether the rules we infer from our visible patch represent the full picture. The early universe provides clues of its own. When you look at the faint microwave radiation left over from the early cosmos, you see tiny temperature variations spread across the sky. These variations give insight into the density fluctuations that later became galaxies and clusters, but they also reveal patterns that hint at the shape of space-time itself. Some versions of cosmology suggest that the universe might be flat. Others suggest it might have a slight curvature. The fact that the cosmic microwave background shows such uniformity in opposite directions of the sky, despite those regions never having been in contact early on, led to the proposal of cosmic inflation. Inflation is a rapid expansion that smooths out irregularities and stretches space-time dramatically. It's another example of geometry acting dynamically and revealing clues through its behavior. The edges of the universe's birth carry hints that space-time might have been shaped by processes that no longer occur. They hint at conditions where quantum mechanics and relativity both mattered. They also suggest that the structure of space-time might have been influenced by forces or fields that no longer dominate. These early edges provide a natural laboratory for understanding how geometry behaves under extreme conditions. But they also reveal how limited our tools are for peering into those conditions. The light that reaches us from the early universe has been stretched and dimmed by billions of years of expansion. It provides clues, but the clues are faint and incomplete. Another clue comes from the accelerating expansion of the universe. Something is causing space-time to stretch faster over time. This behavior suggests that space-time contains a form of energy with negative pressure, often called dark energy. But no one knows what dark energy is. It behaves like a property of the vacuum. It shapes the geometry on the largest scales, yet it doesn't interact with matter in any noticeable way except through gravity. That behavior indicates that something about space-time itself contains energy we don't understand. The fact that this energy shapes the entire universe tells us that the geometry we see is only part of the story. Dark energy also raises the question of whether space-time is stable or evolving towards some long-term state. If the expansion continues to accelerate, the universe could become increasingly isolated, with galaxies drifting so far apart that light from one cannot reach another. This would create new cosmic edges. These edges wouldn't be physical barriers, they would be boundaries created by the geometry and the expansion. The shape of space-time would determine what could communicate with what, and the expansion would dictate how the large-scale structure changes over time. Another clue comes from how black holes and cosmic edges might be connected. Some theories propose that the surface of a black hole, the event horizon, might behave like a two-dimensional system encoding the information about everything that has fallen inside. This idea extends beyond black holes. Some versions of cosmology propose that the entire universe might have a similar encoding on a distant surface. If that's true, then the geometry of black holes might provide hints about the geometry of the universe as a whole. The behavior of horizons might be a key to understanding space-time more deeply. As scientists continue to explore black holes, new questions appear. When two black holes merge, the gravitational waves carry information about the curvature that existed during the collision. Those waves contain subtle details that might reveal whether the geometry behaves differently than expected in extreme regions. Every new detection adds another piece to the puzzle, another glimpse into the edges of space-time where the theories strain against their limits. And as the universe continues to expand, the cosmic edges drift farther away, creating a changing boundary of what we can see. This boundary isn't fixed, it moves as space-time stretches. The behavior of that boundary offers clues about how geometry evolves. The fact that we can only study a finite region doesn't stop us from inferring the presence of structures that lie beyond it, but those inferences depend heavily on the assumptions we make about geometry. The farther we look, the more we rely on theories that might themselves be incomplete. All of these clues, scattered across black holes and cosmic edges, point toward the same idea. The universe contains places where our current understanding falters, where relativity and quantum mechanics collide, where geometry becomes too strange for our tools to handle. These places aren't just curiosities, they're guideposts. They show us where to look next. They show us where the boundaries of knowledge sit, and they prepare us for the next areas of inquiry just outside our current reach, letting the exploration continue onward. There's a certain challenge that appears when you try to make sense of something the universe refuses to display directly. Many parts of physics feel approachable because they let you see what's going on, either with your eyes or with instruments that extend what eyes can do. You can watch a pendulum swing, you can track the motion of planets, you can record the spectra of stars. All of those things give you information in ways that feel accessible, even if the underlying explanations are complicated. But there are regions of reality where nothing is visible, nothing cooperative, nothing willing to reveal itself in the usual ways. You're left trying to understand phenomena that never show you their full picture and sometimes show you nothing at all. This difficulty becomes especially obvious when dealing with spacetime itself. Because spacetime provides the structure in which everything happens, it hides behind the events it organizes. It shapes motion, directs light, and determines how time flows, but it doesn't emit light or leave obvious marks. You can't point to spacetime on its own. You can only infer its presence by watching how objects behave inside it. That means that whenever something unusual happens in spacetime, understanding it requires interpreting indirect clues rather than observing it head-on. And the more extreme the conditions become, the more the clues fade until you reach a point where you're looking at the universe through a layer of uncertainty that refuses to lift. One of the most familiar places where this challenge shows up is inside black holes. You can't see the interior because no information escapes beyond the event horizon. Even light, the fastest messenger in the universe, cannot outrun the curvature. If you were outside the black hole watching an object fall in, the object would appear to slow down and dim until it essentially froze in place right at the horizon. But that's only how it looks from your vantage point. The object itself would continue falling inward, without noticing the moment it crossed. Its viewpoint and yours diverge completely, and because the interior becomes invisible, scientists must rely on mathematical predictions rather than direct observation. This makes the interior one of the most inaccessible regions imaginable. Another place where invisibility becomes an obstacle is in the early universe. The first moments after the Big Bang were so dense and so hot that light couldn't travel freely. It bounced off particles in a dense fog of matter and radiation. Any direct view of that early period is blocked. The light from that time only became free to travel hundreds of thousands of years later, once the universe had cooled enough for atoms to form. This freed light still exists today as the cosmic microwave background, but it doesn't show the earliest times. It shows a snapshot after the universe had already expanded significantly. So the era where quantum mechanics and gravity both operated at full strength remains hidden. Models can describe it. Mathematics can trace the patterns. But direct observation is impossible. Dark matter creates its own form of invisibility. Galaxies rotate in ways that imply far more mass than the visible matter can account for. Galaxy clusters move as though pulled by an unseen gravitational structure. The bending of light around clusters reveals mass that emits no radiation at all. Every piece of evidence points to a substance that has mass, shapes geometry, and interacts gravitationally, but does not emit, absorb, or reflect light. Since dark matter doesn't interact with electromagnetic radiation, you can't see it in the traditional sense. And because it doesn't collide with ordinary matter in noticeable ways, you can't touch it or detect it directly with current instruments. You only know it's there because the things you can see behave as though something invisible is influencing them. Dark energy is even more elusive. You know it exists because the universe is expanding at an accelerating rate. That acceleration means something is causing spacetime to stretch faster over time, but the something can't be observed. It doesn't form structures. It doesn't radiate. It doesn't cluster. It doesn't behave like any known force. It acts everywhere uniformly, yet refuses to reveal any specific form. Scientists infer its presence through indirect measurements of the expansion rate and through comparisons of observed patterns with theoretical models. But dark energy remains invisible not just visually but conceptually too. It doesn't fit neatly into any existing framework. It's an unseen influence shaping the larger scales of the universe. Quantum fluctuations add another layer of invisibility. At extremely small scales, particles and fields behave unpredictably. They pop in and out of existence. They fluctuate in ways that cannot be pinned down. These fluctuations influence the universe, but they do so at scales too tiny to observe directly. Instead, their presence is inferred indirectly through small shifts in energy levels or subtle patterns in field behavior. You never see the fluctuations themselves, you see their consequences, and because the consequences are often faint, isolating them requires enormous precision. Even the curvature of space-time itself isn't visible. You can't look at a region of the universe and see the curvature directly. You can only see how objects move within that curvature. If light bends around a galaxy, the bending gives you information about the shape of the geometry. If clocks tick differently near a massive object, the timing difference reveals how time is influenced by curvature, but the curvature remains hidden behind the behavior it causes. The geometry doesn't announce itself. It remains silent, always present but never directly detectable. Measurement tools also become part of the problem. If you build an instrument to detect gravitational waves, the waves stretch and compress the instrument itself. The entire apparatus becomes part of the signal. You're measuring something that changes the very tools used to measure it. That creates a situation where the thing you're trying to detect refuses to give you a stable reference point. The slightest vibration, the tiniest shift in curvature, becomes a source of noise or distortion. It's incredible that instruments like LIGO can measure gravitational waves at all. They detect changes smaller than the width of a proton, yet even these measurements rely on indirect inference, because the waves themselves are not visible. Then there are the regions of space-time that are inaccessible simply because of distance. The speed of light limits how far we can see. The expansion of the universe pushes distant galaxies beyond the reach of their own light. Even if the universe continues infinitely, we will always see only a finite region. That means vast portions of the universe remain invisible forever. Nothing from those regions can reach us. They exist beyond our cosmic horizon, unseen and permanently hidden. Their behavior could be similar to what we observe locally, or it could differ in ways we can never confirm. Our knowledge is inherently restricted by the nature of space-time itself. These limits become even more pronounced when you consider that many cosmic structures disappear from view as the universe expands. Over time, as galaxies move farther apart, some will cross the boundary where their light cannot overcome the expansion. They will still exist, but they will no longer be visible. The universe grows more isolated as this happens. The edges of what we can observe shrink relative to the entire universe. Future observers, billions of years from now, might see a sky with fewer galaxies. The clues we rely on to understand space-time will gradually fade as cosmic expansion carries objects out of reach. Another challenge arises from the simple fact that looking far into space means looking far into the past. Light takes time to travel. When you observe a distant galaxy, you see it as it was billions of years ago. You cannot see its current state. That means the visible universe is a patchwork of different eras. Some galaxies appear as they were in the early stages of formation. Others appear in mature stages. Some might have already collided or transformed in ways we will never witness. The present-day universe remains partially hidden because the light from those regions hasn't reached us yet. This time delay complicates efforts to understand space-time evolution. You can see pieces of the puzzle, but the pieces come from different times, making it difficult to form a coherent picture. Observing the universe becomes like watching a movie where the scenes are out of order and many scenes are missing. You can piece together the storyline, but the full picture remains inaccessible. The invisibility extends to the structure of space-time at the smallest scales too. If space-time has a granular or quantum structure, the granularity would be far too small to observe. You would need energy levels so high that trying to observe them would collapse the region you were trying to examine. Anything that extreme produces gravitational effects strong enough to distort or hide the information. The very thing you're trying to see would disappear as you approached it. This creates a barrier preventing direct observation of the smallest scales. Even the shape of the universe as a whole remains hidden. The observable region might look flat, it might look curved, but that visible patch is not the entire universe. It's only what light has been able to show us. Beyond that boundary, space-time could curve differently. It could take on shapes that defy our current models. But because we cannot see beyond the cosmic horizon, those possibilities remain speculative. The true shape could be infinite, finite, looped, open, closed, or something we haven't imagined. The clues we have are weak compared to the vast regions that remain unseen. The trouble with trying to observe the unseen becomes even more apparent when considering the behavior of energy and vacuum fluctuations. The vacuum of space is not empty. It teems with activity at the quantum level, but because the fluctuations happen so quickly and at such small scales, instruments cannot capture the underlying motion. Instead, experiments detect averages or effects integrated over time. That means the true nature of the vacuum is hidden behind statistical behavior. The raw fluctuations remain invisible. Another invisible layer comes from the limitations of human perception. Our senses evolved to navigate environments filled with solid, visible objects on Earth. They didn't evolve to detect curvature or fluctuations or exotic fields. Even when instruments reveal these things indirectly, interpreting the results requires mathematical translation. The true nature of what's happening remains outside our intuitive reach. We rely on equations, not sight. We rely on inference, not direct experience. That creates a permanent gap between what the universe is and what we can observe about it. This gap doesn't mean the universe hides out of malice. It simply means that the tools available to living beings in a universe governed by relativity and quantum mechanics are limited by those same laws. Light takes time to travel. Gravity bends paths. Quantum uncertainty restricts measurement. Expansion stretches distances faster than information can cross them. All of these constraints shape the ways we interact with reality. Even the structure of time creates invisibility. You can't see the future. You can't directly observe what hasn't happened yet. Predictions rely on theories, and those theories rely on measurements from the past and present. Whether space-time will continue expanding at the same rate, whether dark energy will change behavior, whether the geometry will shift over unimaginable timescales, all of these things lie outside direct observation. The universe reveals its past to us through light and motion, but its future remains hidden behind a veil of possibilities. This accumulation of invisibilities, black hole interiors, early universe conditions, distant cosmic regions, dark matter, dark energy, vacuum fluctuations, quantum scales, true cosmic shape, future evolution, creates a landscape where understanding requires reaching far beyond what can be seen. Every major theory in physics tries to fill the gaps. Relativity handles the large-scale behavior. Quantum mechanics handles the small-scale behavior. Cosmology bridges the early universe. Astrophysics interprets distant light. But each field relies on clues rather than direct evidence. There's a point in this exploration where the questions stop feeling like they're aimed at the universe and start feeling like they're aimed at us. Up to now, it has been natural to treat space-time as something the universe provides, an ingredient we accept as part of the background. It feels like the kind of thing that should exist whether or not anyone is around to think about it, the way gravity works or the way light travels. But once you spend enough time looking at the pieces that don't fit together and the clues tucked into the places we cannot see, the question naturally shifts. You begin to wonder whether space-time is actually the basic fabric of reality, or whether it's something we constructed as a framework to make sense of the world. Not a fabrication or a mistake, but a model built around the conditions we can observe, shaped by the limits of what our senses and instruments can detect. That possibility opens the door to another way of seeing the universe, one where space-time isn't the foundation but a layer of description resting on something deeper. What makes this question interesting isn't the idea that space-time might not be real, it's the idea that it might not be fundamental. Something can be completely real while still being secondary to something else. Temperature is real, but it's not fundamental. It emerges from the motion of particles. Pressure is real, but it's composed of forces between molecules. Even something like color, which feels intuitive, is an interaction between certain wavelengths of light and biological mechanisms. In each case, the phenomenon is real and useful, but it isn't a building block. It's the behavior of something else expressed through different scales. When physicists consider whether space-time is fundamental or emergent, they mean something similar. They're not questioning whether space-time exists in the ordinary sense. They're asking whether it's the most basic level of description, or whether its geometry, its curvature, and its properties arise from deeper interactions we haven't yet identified. If space-time turns out to be emergent, then the smooth curves, the bending near massive objects, the stretching of cosmic expansion, and the flow of time itself could all be the result of hidden structures shaping the universe behind the scenes. One of the first motivations for asking this question comes from the difficulties we face when trying to merge relativity and quantum mechanics. When two theories work beautifully on their own, but collapse into contradictions when combined, it often means the common layer we assume they share is the wrong one. If space-time were fundamental, then both theories should connect naturally through it. But they don't. They treat space-time in incompatible ways. Relativity lets it bend and stretch. Quantum mechanics relies on fixed backgrounds and doesn't bend its version of time and space. That mismatch hints that space-time might be a convenient model, but not the ultimate structure. The behavior of quantum entanglement reinforces this suspicion. Entanglement creates connections between particles that remain coordinated regardless of distance. These connections don't weaken over light years. They don't care about the geometry of space-time. They seem to obey rules that operate independently of distance entirely. Some physicists have suggested that entanglement might be more fundamental than geometry. In other words, the connections between quantum states might give rise to the structure of space-time rather than the other way around. If that's true, then space-time could be a product of relationships between quantum systems, not an ingredient of reality by itself. This idea gained more attention when scientists noticed something surprising in the mathematics of quantum fields and black holes. Some models showed that the surface area of a black hole's boundary encoded information about the interior. The amount of information that could fit inside the black hole wasn't proportional to its volume but to its surface. This was the opposite of what you'd expect from ordinary three-dimensional space. In everyday experience, the amount of information you can pack into something depends on the space inside it. But in these extreme regions, the information seemed tied to a surface instead. That suggested a new way of thinking about reality. Maybe the three-dimensional world is a kind of projection of information stored on a two-dimensional boundary. Not an illusion, but an emergent structure that comes from something with fewer dimensions. That idea led to the concept sometimes referred to as holographic descriptions of the universe. It's not a claim that we live in a hologram in the science fiction sense. It's the idea that space-time and the objects within it might arise from deeper information encoded in a different kind of structure. In that case, space-time wouldn't be the most basic layer. It would be a higher-level behavior emerging from something more abstract but more fundamental. This remains a theoretical possibility rather than a confirmed description. But the fact that the mathematics works in certain models suggests that our usual picture of space-time might be too limited. Another reason to wonder whether space-time is emergent comes from the behavior of gravity. If gravity is actually the curvature of space-time, then it isn't a force in the same sense as electromagnetism or the strong force. It's a geometric effect. But if geometry is emergent, then gravity would be emergent too. Some scientists have explored this idea and found hints that gravitational behavior can arise from statistical processes, much like temperature arises from countless molecules moving chaotically. In these versions, gravity becomes a large-scale effect created by underlying microscopic interactions. The geometry we see is the average behavior of some deeper system. Even if none of these ideas turn out to be correct, the mere fact that they're plausible suggests that space-time might not be the bedrock we once thought it was. Instead of being the fabric everything is built from, it might be a layer of description that becomes accurate only when we look at the universe at a certain scale. At larger scales, geometry becomes smooth. At smaller scales, if space-time is emergent, the smoothness would dissolve into something more granular or more abstract. That would match the difficulties encountered in trying to measure extremely small distances. The universe resists being examined below a certain threshold, as if the concept of distance itself breaks down once you reach that level. Another way to approach the question is to consider how essential space-time is to our understanding of motion and location. Human experience naturally depends on spatial relationships and on the flow of time. The brain evolved to navigate a world where these concepts are indispensable, but whether those ideas reflect the deeper structure of reality is another matter. Our minds shape the models we build. The models shape our understanding. It's entirely possible that space-time is the structure we noticed first, because it's the one we can perceive most directly. But a deeper structure might be responsible for creating the familiar properties of distance, direction, duration, and causality. There's also the issue of what counts as real in physics. Many things once thought fundamental turned out to be composite. Atoms were once considered indivisible. They turned out to be made of protons, neutrons, and electrons. protons and neutrons turned out to be made of quarks, space could follow a similar pattern. What appears continuous and solid at one scale might break down into more fundamental pieces at another. Those pieces might not resemble geometry at all. They could be algebraic structures, networks of connections, information patterns, or something entirely outside current imagination. When physicists explore these possibilities, they often rely on mathematical consistency rather than direct observation. The absence of experimental access to extremely small scales forces them to use theory to explore what might lie underneath. Some approaches imagine space-time as a network of discrete nodes connected in specific patterns, where geometry emerges when many nodes behave together. Other approaches imagine space-time arising from entanglement patterns in quantum states. Yet others treat space-time as something that appears only when certain symmetries break. These ideas differ dramatically, but they share one feature. None of them treat space-time as the root layer of reality. All of them propose ways it could arise from something simpler or more fundamental. Another clue comes from the way time behaves differently in different theories. In relativity, time is part of space-time and depends on gravity and motion. In quantum mechanics, time isn't tied to geometry. It sits as an external parameter that moves forward at a steady rate. If space-time were fundamental, you would expect a single, unified treatment of time. But the universe doesn't present one. This discrepancy suggests that time might not be the foundation of reality. It might instead be something that emerges when certain conditions arise. If time emerges, then space-time cannot be fundamental either, because space-time includes time as one of its dimensions. Even the expansion of the universe raises questions. If space stretches, what exactly is stretching? If space-time were fundamental, the answer might be straightforward. But if space-time emerges from something else, the expansion becomes the behavior of a deeper system, responding to some underlying rule. The accelerating expansion caused by dark energy could then reflect properties of that deeper structure, not properties of space-time itself. In that case, dark energy wouldn't be a mysterious component of space-time. It would be a sign that space-time is only one of the layers shaped by the deeper rules. Another idea that drives the question forward is the fact that many attempts to unify physics remove space-time from the basic starting point. In string theory, the fundamental objects aren't points in space-time but vibrating strings whose interactions produce space-time. In loop-based approaches, space-time is quantized and emerges from discrete structures. In information-based approaches, space-time arises from entanglement patterns. In causal set theory, space-time emerges from networks of events ordered by causality. In each case, the idea of space-time appears later in the theory, not at the beginning. This placement suggests that space-time is a high-level structure, like the surface of water, which appears smooth even though its underlying components are not. This doesn't diminish the importance of space-time, it simply reframes it. Just as water still exists even though it's made of molecules, space-time would still exist even if it's made of something else. It would remain the environment where planets orbit, where light travels, where galaxies evolve, and where time moves forward. But it would no longer be the deepest truth. It would be something that forms when deeper elements arrange themselves in particular ways, something that reflects larger-scale behavior rather than fundamental nature. What makes this possibility so intriguing is that it aligns with many of the places where relativity and quantum mechanics disagree. If space-time is emergent, then the contradictions between the two theories might stem from using a model that works perfectly in one domain but not in another. Relativity describes the emergent geometry well when the scale is large. Quantum mechanics describes the underlying structure well when the scale is small. But when you try to push relativity into the domain of quantum mechanics, it reaches its limits because it's describing something that no longer exists in its usual form. And when you push quantum mechanics into regions governed by curved geometry, the model breaks because it doesn't account for the emergent nature of that curvature. All of this leads to the larger idea that space-time might be a bridge rather than a foundation. A bridge between the deeper rules and the observable universe. A bridge between the hidden structures we can't see and the physical behavior we can. And the existence of that bridge could explain the mismatches, the paradoxes, the infinities, and the puzzles that appear throughout physics. There's a certain kind of anticipation that comes from standing close to an answer without being able to step all the way into it. Scientists reach that point often, especially when dealing with the deeper structure of the universe. You build a theory, test it, refine it, push it as far as possible, and sometimes it performs almost perfectly. It explains nearly everything you throw at it. It predicts new things with remarkable accuracy. It becomes the lens through which generations look at the universe. Yet there's always a moment, especially in fundamental physics, where you stretch that theory just a little too far and watch it begin to strain. The surface starts to crack. Numbers stop lining up. Patterns begin to blur. It becomes clear that the theory that almost explains everything has a boundary of its own. This is where many of today's ideas sit. They do an impressive job describing enormous ranges of physical behavior. They shape the way we understand nearly every part of nature. But when you place them next to the biggest questions, especially the ones that involve combining quantum mechanics with gravity, they fall just short. They offer partial answers but no complete picture, and that near-miss quality becomes one of the most intriguing parts of the search for a deeper understanding of space-time. The most established example is the pair of theories people rely on every day, general relativity and quantum mechanics. Each one explains a huge part of the universe. General relativity handles gravity, cosmic expansion, black holes, and the curvature of space-time. It's precise, elegant, and astonishingly predictive. Quantum mechanics handles particles, forces, fields, and the probabilistic behavior that governs matter on tiny scales. It has been tested more thoroughly than any other idea in science. But as accurate as both theories are, they don't join into a single unified description. They come close, and in many places they overlap beautifully. Yet in the regions where both should apply, especially at extremely small scales near intense gravitational fields, they contradict one another. Some theories try to merge them from the top down. Others start from smaller building blocks and work upward. But each approach has struggled because gravity behaves differently from the other forces. Attempts to quantize gravity create equations that explode into infinities. Attempts to describe particles purely in geometric terms fail to capture the restless nature of quantum fields. Even attempts to treat time consistently across both theories run into trouble. In relativity, time depends on motion and gravity. In quantum mechanics, time stays fixed. That mismatch alone becomes a major barrier. One of the earliest attempts to combine everything into a single theoretical structure came from the idea of unification. People noticed that electromagnetism and certain interactions could be described together if they were treated as part of a larger underlying symmetry. This led to the development of theories that combined forces at high energies, showing that the differences between forces might only appear at large scales. At extremely high energies, near the conditions of the early universe, the forces could merge. This idea became known as grand unification. It suggested that the fundamental interactions we see today were once part of a single system. But the theory still didn't include gravity, and it required energies far beyond anything we can reach experimentally. Then there's the standard model of particle physics, a framework that describes the known particles and forces except for gravity. It has been enormously successful. It predicted particles before they were discovered. It explained countless interactions. It organized matter into elegant families and symmetries. But even with all its successes, it leaves major questions unanswered. It doesn't explain dark matter. It doesn't explain dark energy. It doesn't include a mechanism for gravity. It doesn't clarify why the constants in the equations take the values they do. It works brilliantly, but only within a specific range. Another avenue that emerged was the idea of extra dimensions. If space-time had more than the familiar four, maybe gravity behaved differently because it extended into those additional dimensions. This approach showed that gravity could appear weak in our observable universe if some of its influence leaked into hidden dimensions. The mathematics worked nicely in certain models, making gravity seem small in familiar space but strong in others. But despite the appeal, no direct evidence of extra dimensions has been found. And even if they exist, it remains unclear whether they help unify gravity with quantum mechanics in a complete way. Then came the idea of string theory. Instead of treating particles as points, this theory imagines them as tiny vibrating strings. The type of vibration determines the particle. In that framework, gravity emerges naturally, because one of the vibration modes behaves exactly like the graviton, the hypothetical quantum of gravitational interaction. This was one of the first theories to incorporate both gravity and quantum mechanics without generating uncontrollable infinities. It inspired enormous interest because it created a unified picture of all particles and forces, but it also required extra dimensions, specific symmetries, and structures that haven't been observed directly. And because the strings are so tiny, it's nearly impossible to test the theory experimentally. It remains elegant, promising, and incomplete. Closely related versions of this idea explore the possibility that space-time itself arises from deeper objects called branes, or from fields defined on lower dimensional surfaces. In some cases, the mathematics suggests that the universe we see could be the boundary of a higher dimensional space. In others, the geometry of space-time emerges from networks of quantum states. These concepts provide potential bridges between quantum mechanics and relativity, but they remain theoretical. They almost explain everything, but not quite. Another approach takes a different path altogether by trying to quantize space-time directly. Instead of smoothing space-time into a continuous surface, these theories propose that space-time has a discrete structure at the smaller scales. One example comes from loop-based approaches, where space-time is composed of tiny loops woven together into a network. The loops create a geometry that looks smooth at large scales but becomes granular at tiny ones. This avoids the infinities that appear in other attempts to quantize gravity. It provides a natural explanation for why certain quantities remain finite in extreme regions, but the theory is challenging to test, and while it describes many features of gravity, it doesn't yet unify gravity with the other forces. Another near miss emerges from approaches that treat space-time as a network of events connected by causal relationships. In these models, space-time doesn't exist until events occur. The relationships between events create the geometry. This removes the need to treat space-time as a continuous background, which helps avoid contradictions with quantum mechanics. But turning causal relationships into smooth geometry requires many assumptions, and the connection to observable physics remains tentative. Some ideas approach the problem from the direction of information. Instead of treating space-time as a physical object, they treat it as something that emerges from the way information is stored and shared among quantum systems. In this picture, entanglement doesn't just connect particles, it shapes geometry itself. Distances emerge from how strongly states are linked. Curvature emerges from how information flows. These ideas are mathematically compelling, and they link several puzzling features of black holes and quantum fields. But they're still young. They haven't yet been shaped into a testable theory that explains all known physics. Even inflation, which explains many features of the early universe, has gaps. It describes how the universe expanded rapidly shortly after the Big Bang, smoothing out irregularities and producing the uniformity we observe. It predicts the patterns in the cosmic microwave background and explains why space appears nearly flat. But inflation requires specific conditions to begin. Those conditions aren't explained by the theory itself, and inflation predicts a variety of possible universes depending on the details. That raises the question of whether the theory is describing fundamental physics or just one version of a broader set of possibilities. Quantum field theory, the framework that underlies the Standard Model, also reaches its limits. It describes particles and forces as excitations of fields spread across space-time. It works extraordinarily well. But when you try to apply it in curved space-time, especially near black holes or during cosmic expansion, new puzzles appear. The theory suggests that the vacuum isn't empty but filled with fluctuations, but the amount of energy predicted by those fluctuations is far too large. If the prediction were accurate, space-time would curve violently. But it doesn't. Something about the combination of vacuum energy and gravity refuses to align. Supersymmetry offered another possible extension. It pairs every known particle with a heavier counterpart. If supersymmetry were real, it could solve several problems at once. It could explain dark matter. It could stabilize the vacuum. It could unify forces at high energies. But despite decades of searching, no supersymmetric particles have been found. The idea remains mathematically elegant but experimentally unconfirmed. Then there's the ongoing puzzle of dark matter itself. Some theories propose that dark matter is made of undiscovered particles. Others suggest that gravity behaves differently on large scales. Modified gravity theories attempt to explain galactic rotation without invoking dark matter. These theories produce interesting results, especially in specific systems, but they struggle to explain all the evidence consistently. They almost explain everything, but not quite. Even the idea of unifying all forces into a single framework encounters obstacles. Each attempt requires conditions that may not exist in reality, or relies on energies we cannot access. And when trying to push these theories into regimes where quantum mechanics and gravity collide, the mathematics becomes tangled. The theories predict particles we haven't found or behaviors that conflict with observation. Their beauty often comes from mathematical consistency rather than empirical success. These near-miss theories reveal something deeper. The universe isn't failing to provide a final answer. The theories are showing where their strengths and weaknesses lie. Each one captures a part of the picture. None captures all of it. That suggests that the truth might lie in a combination of ideas rather than a single, tidy solution. Or it could mean that the next breakthrough requires a completely new viewpoint, something that reframes space-time and its relationship to matter, energy, and information. Despite their limitations, these theories guide scientists closer to the point where the missing piece might appear. They reveal patterns that repeat across different models. They show which features are essential and which are artifacts of the mathematics. They teach researchers where contradictions arise and where assumptions no longer hold. There comes a point in any long exploration where the questions begin shifting their tone. They stop feeling like puzzles to be solved and begin feeling like invitations to look more closely, like gentle reminders that understanding isn't always about reaching the end of something. In physics, especially the physics dealing with space-time, quantum behavior, and the nature of reality itself, that shift arrives quietly. You spend so much time following theories that nearly work, examining ideas that come close to explaining everything, and trying to resolve contradictions that refuse to settle, that eventually the path ahead becomes less about what is known and more about the landscape of possibilities spreading out in front of you. It becomes a place where uncertainty isn't a roadblock but a guide, steering you toward areas that might reveal something new. One of the first things you notice when thinking about the future of physics is that it rarely moves in straight lines. Each major idea from the past century emerged not as the next obvious step, but as something that surprised almost everyone who encountered it. Relativity rewrote the rules of space and time. Quantum mechanics shattered any notion of predictable certainty. Cosmology revealed that the universe was expanding. Dark matter hinted at invisible mass-shaping galaxies. Dark energy introduced a force stretching space-time in ways no one had expected. None of these discoveries lined up in a tidy sequence. They emerged from experiments, mathematical questions, or contradictions that forced people to look beyond familiar assumptions. So when you imagine what the future might hold, the safest expectation is that it won't follow the patterns we currently consider natural. The challenges that lie ahead are immediate and deep. The tension between quantum mechanics and gravity remains unresolved. The nature of dark energy is still an open question. The identity of dark matter is unknown. The early universe hides behind a curtain of opacity. Black hole interiors remain inaccessible. The quantum structure of space-time, if it exists, has not yet been detected. Each of these issues points toward a gap in our understanding, suggesting the existence of something more fundamental waiting beneath the surface. But none of these gaps tell us clearly what direction to take. They only indicate the boundaries of what our current models can handle. One possibility for the future involves building a theory that unifies everything into a single coherent framework. People have been trying to do this for decades. The appeal is obvious. If the laws of nature arise from a common foundation, then the mismatches we see today could be resolved naturally. A unified theory would describe gravity and quantum mechanics together, explain the origin of space-time, reveal the nature of dark matter and dark energy, and provide a consistent picture of the early universe. But the difficulty lies in the fact that each step towards such a theory introduces new complexities. The mathematics becomes harder to interpret, the physical implications become more abstract, and the distances between prediction and observation grow wider. Even so, the search continues because the match between patterns across different areas hints that unification remains a reasonable goal. Another possible direction comes from the idea that the universe might be understood better through information than through matter or fields. Information-based approaches propose that everything in the universe, including space-time, arises from underlying informational processes. Entanglement, causality, symmetry, and probability become the fundamental ingredients. Geometry emerges not from physical objects but from the way information is structured and shared. Put this way, the universe becomes something like a network of relationships, where the shape of space-time reflects the strengths and weaknesses of those relationships. If this path leads to a deeper theory, it could explain why entanglement plays such an important role, why black hole information behaves the way it does, and why space-time seems flexible rather than rigid. There are also approaches that imagine the future of physics requiring an entirely new conception of time. Right now, time is treated differently in different theories. In relativity, it is a dynamic dimension woven into space-time. In quantum mechanics, it is an external parameter that moves forward at a steady rate. This mismatch might be hiding something important. Some future theory might reveal that time is not fundamental at all, but something that appears only in certain conditions. Perhaps time is emergent, arising from statistical patterns, entanglement structures, or deeper symmetries breaking at large scales. If this turns out to be true, the flow of time could be more like the flow of temperature or pressure, not a basic property of reality, but a behavior that emerges from many interactions working together. There's also the possibility that the universe contains structures or objects we haven't discovered yet, ones that don't fit into any of the categories we've established so far. When scientists talk about dark matter, they often assume it will eventually be identified as a particle. But it could be something entirely different, such as a new kind of field, a modification of gravity, or a sign that the structure of space-time changes at large scales. Dark energy might not be a form of energy at all, but a sign of some larger process shaping the geometry of the universe over time. These unknowns hint that the future might involve rethinking the categories we take for granted. Another direction might come from studying the smallest possible scales more closely, not through direct measurement, but through theoretical advances that reveal how space-time behaves when distances shrink far below what we can observe. At those scales, quantum fluctuations could dominate. Geometry could dissolve into something unpredictable. Distances and durations might no longer have meaning in the traditional sense. The familiar picture of space-time might be replaced by something more discrete, more dynamic, or more relational. If this happens, many of the contradictions between relativity and quantum mechanics could resolve themselves naturally. The apparent incompatibility might stem from trying to describe smooth geometry in conditions where smoothness breaks down. There's also a growing sense that the next major breakthrough might come not from physics alone, but from mathematical structures that have not yet been applied to physical theories. Many past discoveries emerge from mathematical insights that didn't initially appear connected to physical reality. Non-Euclidean geometry seemed purely theoretical until it described curved space-time. Complex numbers seemed abstract until they explained quantum wave functions. Group theory seemed esoteric until it organized the symmetries behind fundamental particles. Today, there are entire areas of mathematics that haven't yet found their physical application. As more ideas intersect, the future might involve structures that make the behavior of space-time, quantum fields, and cosmological evolution look like natural consequences of a deeper mathematical environment. There's also the possibility that the future will require a shift in perspective rather than new equations. Humans naturally imagine the universe in spatial terms. We rely on visual thinking, intuitive geometry, and spatial relationships to make sense of the world. But space-time at the smallest or largest scales might not behave in ways that match those intuitions. The future might demand thinking in ways that don't rely on familiar concepts. This could mean visualizing reality as something more network-like or process-based. It could mean focusing on relations rather than objects. It could mean understanding fields not as substances filling space, but as manifestations of deeper layers we haven't conceptualized yet. Even the idea of causality may be revisited. In everyday life, cause leads to effect in a straightforward chain, but quantum mechanics challenges this simplicity. Some processes appear to lack a clear order. Entangled states behave as though they share information outside of ordinary causal chains. In some theoretical frameworks, causality itself emerges from deeper principles rather than existing as a foundational rule. If the future reveals that causality is not an absolute structure, but one that appears only in certain regimes, it could change how we model the universe at every level. Observational advances will also play a significant role in shaping the future of physics. New telescopes, detectors, and instruments will provide data from regions previously inaccessible. Gravitational wave observatories may grow more sensitive, capturing waves from the early universe or from objects that test the limits of relativity. Particle accelerators might discover new particles or rule out entire classes of theories. Space-based detectors may reveal subtle shifts in cosmic expansion or uncover patterns in gravitational fields that point toward new physics. Each new piece of data becomes a stepping stone toward whatever theory comes next. But even with better technology, the universe imposes limits. We can only see as far as light can travel. We can only measure as deeply as quantum uncertainty allows. We can only infer structures that produce observable effects. Large portions of reality may remain forever beyond our observational reach, yet even those limits can help guide theory. They tell us where the gaps lie, they reveal where the models begin to falter, and they show us the types of explanations that might work across those boundaries. Another important shift in the future might involve accepting that some questions do not have single, straightforward answers. The universe might not be built from a single unified structure. It might be composed of layers, each with its own rules, each emerging from the one beneath it. Spacetime might emerge from quantum processes. Quantum processes might emerge from symmetries. Symmetries might arise from even deeper patterns, and those patterns might not resemble anything we consider physical in the traditional sense. If this layered view becomes central, the future could focus on understanding how each layer connects to the next, creating a more flexible picture of reality. Thinking about the future of physics also means accepting that some of the ideas currently considered fringe or speculative might become mainstream. Many revolutionary ideas began as speculative. Quantum mechanics was once controversial. Relativity was once considered radical. The expansion of the universe was once doubted. Theories that seem unconventional today could become the foundation of tomorrow. Their current limitations don't necessarily reflect flaws. They might simply reflect the early stages of development. Just as likely is the possibility that the next breakthrough will come from recognizing a pattern hiding in plain sight. Something simple yet overlooked because it doesn't fit the expectations shaped by current theories. Many advances in physics came from small clues that didn't seem significant at first. The slight anomaly in Mercury's orbit led to relativity. The ultraviolet catastrophe led to quantum mechanics. The faint uniform glow of the cosmic microwave background reshaped cosmology. The future might depend on noticing something equally subtle. There's also an emotional aspect to imagining what comes next, a sense of being part of a long process that extends far beyond any single lifetime. Every scientist contributes a small piece. Every measurement adds a fragment. Every idea, even the ones that don't survive, nudges the collective understanding in some direction. The future of physics is not a competition to reach a final answer, but an ongoing collaboration with the universe itself, observing, asking, testing, adjusting, and slowly revealing more of what lies beneath. And as these questions keep expanding, as the theories keep reaching toward deeper possibilities, the path ahead stays open, allowing the exploration to continue.